Hello and welcome back to another video. We just hit 1,000 subscribers, so I want to thank everyone that's new and everyone that's old. And if you're old, that means you've only been with me for 4 months, and if you're new, you've probably been with me for like a day. So I just want to say thanks for everyone for liking and subscribing. Yeah, welcome. Anyways, today I was really wanting to go over some sort of like 3D array. I was really looking at some types of architecture like what MVRDV, what Bjarke Ingels do with sort of these styles of massings. This one's MVRDV. The prior was Bjarke Ingels, and I think this is ODA in New York. Oh yeah, ODA New York. So this is definitely a very contemporary style, and it's coming from the sort of computer graphics world. I just found this nice image that explained it. This ability of capturing in that third dimension an array of what voxels, like a volumetric pixel, and how this sort of is lending itself towards architecture and modular components. You can have similar components and create sort of endless, infinite possibilities of different forms. Something, along the lines of also Minecraft worlds and what they have done. So anyways, I was really trying to do that today. So what we're going to do is we're going to take this geometry, this boundary representation in Rhino, and what we're going to take from that, which it has properties which are sort of these dimensions, the X, Y, and Z, that describe this geometry, which does not have to be a rectangle or a box. It can be anything, but we're going to start out with a box. What we're going to do is we're going to use these X, Y, and Z dimensions to create an array of points in three dimensions. And then what we're going to do with those points is we're going to test for which ones are within that boundary representation. And what that will do is allow for us to determine where to voxelize and where just to remain a point in space that doesn't mean anything. For example, a point out of here does not mean anything for us. And then once we have those points, we can then determine where we're going to voxelize. So this is going to save us a lot of computing power because we're going to be dealing primarily with points, which are just made up of 3 different numbers, X, Y, and Z. And then we're going to voxelize at the end. So it's actually a very lightweight Grasshopper computational method. But and in the end, I'm going to reproduce something along the lines of this, which is similar to the MVRDV project in Moscow, which is a much more complex form, but we can see how it will morph depending on the size of the voxels and where we place that start point for the array that's going to be captured within that geometry. Anyways, let's jump into Rhino now. Okay, now that we're here in Rhino, what I'm first going to do is show you how to create a array. So what I'm going to do is construct the points, and this will now allow you to manipulate their X, Y, and Z direction. So what you're going to want to do is, because we want to create many of these points in an X direction, let's create a series of this. What this is doing is first number in the series, the step size, and then the number of values in the series. So right now it defaults to 0, 10, or 1 step size, and then 10, which we have to zoom in to see because it's pretty small. So what we've done is now we've created, according to that 3D array geometry, we've created that 1D array. So now let's create, how do we make it 2 dimensions? If I just plug this exact same series into the Y, what is going to happen? It's going to now take the first value of the series that we're feeding into the X, which is 0, and the first value from the series that's Y, and it's going to create that one corresponding point. So here we have 0, 0, here we have 0, 0, or 1, 1, here we have 2, 2, 3, 3, and so forth. And so if we repeat the same thing, it's going to add to that, and now we have 1, 1, 1 here, 2, 2, 2 here, 3, 3, 3 here. So it's an easy way of getting this, but this does not create us an array. This just creates us 10 points with the same X, Y, and Z. So what we're going to do here, let me delete this for the Z first. What we need to do is actually we need to graft one of these lists so that it feeds it gives it an extra branch, so that when I plug into here, it now knows that for each one of these X numbers, we need to give it 10 in the Y direction. So now for each in the X, we're getting 10 in the Y. And this has to be repeated again, and we can do it with another component. I'm gonna delete these. So now what we can do is we're gonna move these same points in the Z direction. So we're gonna move, and we need to create another series. We couldn't keep the same series, but just for this sake, we need to add a series in the Z direction. And this is gonna give us a very weird result, because now this Z is not corresponding to what the data of outputting from this construct points is. So if we add another graph, it's still not corresponding. So what we're actually going to need to do is we're actually going to need to graft this point outcoming here. And I mean, we can plug in another graphed component, and then we will finally receive the correct data input, which should be 10 branches of 10 sets, each with 10 points, so corresponding to the X, Y, and then Z direction. And what this will do is now it gives us an array of points that we can start playing with. So this is just an array of points, but what we are going to want to do is, this is in arbitrary space. What you're going to find is you're going to be creating objects that don't necessarily correspond to, that doesn't actually correspond to that point. Not every one of our objects we're going to be creating is starting at 0, 0. So what we're going to want to redo is where this endless array of points is going to start, and we're going to correspond that to our Brep. What we're going to do here, the only two variables we're going to need sort of in this in this example are going to be the Brep and then the size of the voxel. Because other than that, that's going to be, that's it. We can extract the dimensions of all the shape we're going to be making from the Brep, and all we need to know is the density of the points, and therefore the density of the voxels that are going to exist within that Brep. So here on one side, we're just going to need this Brep and the slider that's going to represent here voxel size. Well, first off, we need to find out where this is going to correspond here. We need to have it sort of start out from one point. So we're going to have to choose which point. And I know this Brep right now is a rectangle, but so actually what I'm going to do is I'm going to modify it slightly. So it does have a little bit of complexity. I'm just going to do Control Shift and move this over here. So what we need to do is we're actually going to have to take the bounding box of this Brep here. So what we're going to do is take the B box, which you can just type in BB, and this will create a geometry that encloses that entire surface. And so now we can computationally know that if we populate this bounding box with all the voxels, we'll always be able to be sure that this Brep within it also has those voxels. So instead of just creating an endless array, because I could come over here and take this exact same array and just put, 1 million in this direction, 1 million in this direction, and 1 million in Z. And yes, you are going to find that coincidence between those points inside that Brep, but it's going to be a way more computationally expensive process. So what I'm going to do is I'm going to constrain those where we're going to assign those points to within this bounding box. So let's deconstruct this bounding box, deconstruct Brep, because it does come out as a Brep. Because I want to take one face, so we have the faces here, which I'm going to list item, and we can come in here, and I know there's going to be 6 sides to this. So there's the first one, there's the second one, there's the third one, there's the fourth one. I'm actually going to hide preview off so I know which one I'm selecting, because I want to grab the bottom one to find the X, Y, and or the X and Y dimension. Wait, I think it's supposed to be the fourth one. So I can just take a surface and plug this in. And yes, okay, so that's it. So I can turn this all off. So now I have, because first, before I can even bother with the Z, as I showed you in this, this little example up here, we need to first know the dimensions of the X and the Y. And this is going to be pretty easy because we can just take a dimensions tab of a single flat surface. And now it's going to give us two values, which can be known as the X and the Y, or U and V in this scenario, because it's evaluating a surface. So now we know this, but we also need a start point for the grid, which I can just evaluate the surface. So I can evaluate the surface, and this will give us, and we can plug in a multi-directional slider to know, to say where to evaluate the surface. And this does look like it's going at that bottom corner, but actually what you're going to find is it's actually not exactly on the bottom left corner. So what I'm going to do, it's because I need to reparameterize this. And what that'll do is now this is corresponding with, it remaps the values 0 to 1, 0 to 1. So on this MD slider, I can accurately represent, without knowing the size, the exact size, I can give it a good base point. So if we just move it to 0, 0, now we have a exact starting position in that corner. And there's of course a million ways to do all of these things. I'm just showing you one example, and one that I find quite common. So right here, now we have a point, or that we're going to use for starting points. And then, okay, so what we need to do is we're going to need to be dividing these numbers and tell us how many voxels we need to array in each direction. So let's first just break down one of these, and we'll call it like the X dimension, which I think is the V, which is the longer of these two. Okay, so so this is the X dimension, and what we're seeing here is it's 144 because it's the second one. I mean, if we just plug that in, yeah, we can see it's 144. So what we're going to take is we're going to actually divide that 144 by the voxel size, which we are going to give. And what this is going to do is Control C, Control V. What this is going to give is the number of voxels that are going to be needed to represent that entire length. So we're going to need 28.85, which I believe we should just use. So we're going to have to round this to an integer because you can't have 0.85 of a voxel or a point. So we can just round this to, and it'll give us the nearest, the floor, and the ceiling. In this case, so here I can just quickly show you what it means. Nearest is 29. The floor should be the integer that's below, so it'll always round down. So this should be 28, and ceiling will also be 29, I believe. Yes, 29. So now we have that number. So we now know how many voxels we need to move in the X direction. I can show you what the floor and the ceiling will all do. So we need to, in the same method, we need to construct a point, graft it, and construct a point and move it in the X direction. So we can do a series. So this series is going to create that. So we're going to start with 0, with step size for each successive number. That step size is now going to be that voxel size. And the number of values is going to be that number here. So I'm just going to plug that into here. And now I can take a move component, and now this start point is going to be very important, because what I'm going to do is I'm going to move that this many times in the X direction. Okay, so look, so now what we've done is we've sorted out how many there is. The one thing I am curious about is maybe in this example, I'm actually going to want to use the nearest or the ceiling to more accurately represent that voxel. And this is, I think I'll be able to more clearly explain that, because when we actually build the volumes, it may stick out on these sides depending on which number you're going to input from that rounding. So that is relatively important. Okay, so we pretty easily have found out the number of points we need in the X direction, and we've already arrayed those points based on that voxel size, which we can change, of course, right? So 4, 3, 2, 1, and upwards. Let's maybe put it even a little bit higher, just so this video will speed along and my computer won't lag. Okay, so now we just know from, once again, our previous experience, now we just need to bring in that same series for the Y. So we can do the same exact thing. So here we found the X. Here, I'm just gonna move this up. So we found the X, so now let's find the Y. So we can, Control-C, Control-V can be a little bit of a nightmare, so let's just redo it. So what we're gonna have is we're gonna take that other value, the U dimension, which is 89. We're gonna plug that in here. Same as before, we're gonna divide it by the voxel size. Then we need to round, so I'll just Control-C, Control-V. Let's kind of line these guys up, a little bit of organization. So now we have rounded out. Now let's create that series and a move. A series, we're starting number 0. Step size for each successive thing, which will be the voxel size again. Number of values in the series, what this guy's telling us, so let's just place the floor, and now it's telling us that there's 12 values, so we can now move. So let's move this guy in the Y direction. So now, as you can see here, we have, here, I'm gonna go into ghosted mode so we can see it easier. We can see it more clearly. So now you can see it has moved all those, but we don't actually want to move just that point. We want to move all of these points. So once again, if we do that same exact problem, instead of replacing just that origin point, if we do it like this, we're going to come up with that same exact error. So we're actually going to need to graft this data tree to create that. So now we have a 2D grid that will approximate that. So now let's quickly transform that into the third dimension. This one is going to be a little bit more interesting because we need to figure out how we can know the height of this. So we could take, for example, another one of these surface. For example, Control-C, Control-V, maybe this surface. So this surface, if we measured it, it's going to give us the height of it, which is nice. We could either, for example, we could evaluate that surface. So if I plug that surface into here, and then put the PT on there. If I move this guy around, I can move it up here, and now I know it's at the top, and now we could measure the Z value, and that could tell us the height, which is 79. Or I think let's do it in the same manner as we did here, which is the U and the V here, which when let's plug this guy into here and this guy into here. So as you can see, that the U was that same Y dimension, and it's actually V that in this scenario is going to be giving us the Z height. So right here, I'm going to take from this V. I'm just going to go here and bring that down there. So I know in the future, I'm going to be corresponding with the dimension from that V. So what we can do is we can basically just, this time I am going to actually just copy paste, and let's disconnect. So we're clear as where we need to, this is probably bad practice, just copying and pasting, but if you want to make your scripts fast, then maybe that's nice. Actually, no, that one is accurate. We do need that voxel size in that series. So over here, the division will now be this Z value up here, which you can either connect from the panel or here. Z, so now that's going to round out to be 11. So we know we're going to have 11 voxels in the Z dimension. This is giving us that array number. We know we don't want Y here. Now we need to replace it with the Z vector, which goes in here, and then we can delete the Y. And now we can simply, is it going to work if I, for example, move this into here? Oh, we're going to come up with, again, the same problem. So what I can do is also graph this data tree. And then do it. And now, as you can see, we have points that totally fill out that space. And so quickly, I'm just going to put a rectangle or a box on these pieces, which let's just do box provide 2 points. No, box properties, box rectangle, a rectangle and a height. Let's do create a value box, normalized domain box. Yeah, I think this domain box is going to be the most appropriate. So what we have here is we're going to be a base plane, which we can do, get all these points, and that will be our base plane. And then we're going to have 0 to 2, 0.5 to 0.5. That's the domains that we need to put in here. But I believe that we can just take this voxel height, and if we plug it in here, yep, 0 to 7, it's going to give us that accurate, the accurate dimension. So we just plug this in here. What we're going to need to do though is, so we can do this and see what happens, but I have a feeling we're going to get a lot more boxes. So what actually we're going to do is we're going to flatten this data before it comes in, or we can actually just right click on the B and do a flatten scenario here. And this will give us a clean flat list of all the voxels that occupy the space. But we don't necessarily want that. We do want one more thing. So I'm going to turn this off. There's one more thing before we do that, is we need to test if these points are within that BREP or not. So over here we have that BREP. So point in Brep. Point in Brep. Test whether a point is inside a closed BREP. So what this is going to require is a point BREP for inclusion test, which I can just drag from over here. A point, which again I'm going to flatten prior to putting it in, just because the computer can explode if not. So what this is going to output is a list of patterns. So true, false, true being within the BREP, false being not without. So what we can do is do a col pattern, and what this is going to do is remove from this list. And actually, what I think I'm going to do, let's see what happens if I don't flatten this. So this should still work, because I don't want to flatten it yet, because I need to use the same. If I flatten it here, I also have to flatten it here to get that same the same results. So I don't want to flatten it yet. So what it here, and as we can see, it's already working out. If I went back and go and hide, which I should be doing along the whole time, we can now see that there's only those correct points. And then I can do that cold list of points into here, and voila, we have a nice repeating voxel pattern that you can go and manipulate, whether it's 6, let's do, bring it down to 4. If I bring it too low, my computer's going to crash, and whatnot. So as you can see, that was actually pretty simple, but it just used a very simple concept of that 3D array that we're building computationally to be constrained to the same bounding box, and sort of determine where to voxelize based on that. I think it would be more efficient if, for example, we used meshes here, or we used a block instance, but just for this exercise, yeah, that should be working appropriately. So now what I'm going to do is I'm going to quickly create a more provocative form, and then test the same thing in there. I'm going to create a new layer, and we're going to build something that more resembles an MVRDV building. We're going to try to do it as quick as possible. So we're going to look at this building, which is an MVRDV project in Moscow. And I'm going to quickly build this form, and we're going to apply the same computational process in Grasshopper to a shape that more resembles something like this or this. I'm going to do it also in SubD, just for the sake of it. You don't have to do it in SubD. You could do this easily and just in NURBS, and it would be totally fine. So I Control Shift, let's drag this up. Let's drag this over. And then I realized I'm only gonna want one side of this. So yeah, let's do it like that. Then I'm gonna rotate this based on this corner, and I'm gonna make sure it's a copy so that when I do rotate this, it actually corresponds. And I'm going to now extrude these both up. And I realized I should also extrude these both down. I'm gonna make sure this is starting at 0 M, move. Sometimes Rhino gets started. And then if you type V, it'll always move vertically. And then you can just type in 0 and it'll go down. So it's always starting at 0. Anyways, okay, so let's go like that. Then this guy is going to be mirrored. And then mirrored again. And then all of this is going to be, well, actually, let's quickly, I think if I just bridge these, let's see. Oh, that added in extra faces, which I don't want. Bridge, and then I want to reduce that down to just one segment. I think I'm gonna have to fill hole here. I think there's a fill hole somewhere up here, insert points. Okay, the SubD hole is right here. And if you click on it, then you control shift click on that. You should be able to just fill that in. And for these guys, what I'm gonna do is actually, I'm gonna bridge this, but I'm gonna add one segment. And then I'm going to take that segment and I'm going to move it backwards. Then I'm actually just going to take that point and move it there. And then I'm going to do the exact same for here, which let's do with these guys. Bridge, not bridge with one segment. Okay. And then let's be a little bit accurate. Let's move it. Shift to lock it in one direction, and then we can click there. So now we know we are aligned, and we can now control shift click on that vertice, M to move, and then totally miss it and move it up there. Okay, so now let's see how we're gonna do this. I'm gonna Alt to copy, and then click on this gumball, and then click 180, so I know it just copies and rotates 180 degrees. I'm gonna move this guy to line up with there. And now we're almost done, actually. So I'm just gonna Control J to join. And then we're just gonna need to do a few more simple steps. So we're gonna bridge this guy. And then, well, I guess we can move this. No, that doesn't give us a very nice result. I'm actually going to delete that vertice or that edge. And now we're going to do the fill hole, which is called SubD hole thing. Enter, easy. And then we're going to do the same over here. Reduce down to one segment. And then let's do the fill hole, Control Shift there. And I'm not actually going to be using necessarily this. Let's see what happens if we just fill a hole when it's like that. Oh, that is not what I wanted. Control Z. So let's figure it out. This guy wants to go there. There. Ooh, yeah, there gets a little nasty. So let's just start by bridging these ones. I don't know how great this topology is, but I'm not really using SubD in this instance to be the most topologically correct for subdividing. I'm more just using it as a means of, I'm just filling the hole. I'm using spacebar just to repeat the previous command. And then I'm going to do this again down here, which is bridge. Okay. What I'm going to do is now after that, I'm going to bring this into Grasshopper. And there is one convenient thing about SubD is I can actually just bring in a SubD, assign this guy as a SubD, set1 SubD. I'm going to hide this. What I'm going to do is I can just plug this SubD into a VREP and it instantly converts that to a VREP. And look at that. Here, let me, I'm going to preview these with a custom preview, like that, custom preview. My spelling issues are atrocious. Swatch, color swatch. Let's just bring this guy to like a light gray. Except, blink, blink, okay. So now, if I bring back this SubD, let's get some more resolution in this guy. Let's bring that back to 5. That's a little bit more interesting. And as you can see, we're getting something along those lines of that Moscow project. I think mine's a little bit more ghetto, but nothing that can't be fixed. Anyways, I'm going to let you go ahead and explore more with this. You can convert these, of course, SubD to NURBS and or crease this. Like if I, for example, if I just take this SubD and just grab everything and then crease, and it will take on the original shape. So now when now it doesn't smooth out into that more complex form. Anyways, I just did this in SubD so I could quickly edit, like take all these guys. Oh yeah, you know, actually I want to bring, and then make, you know, or make just this peak a little bit taller, like I think they have in the, like I think they do. So anyways, as you can see, the power of SubD, first off, is insane. And the second off, the power of being able to voxelize and always correspond with correct dimensions and values with only one real input, which is this guy, this voxel size, and what input you have as a geometry is super powerful. Anyways, thanks very much. Thanks for watching. Please leave a like if you enjoy the video, and yeah, subscribe. Thanks a lot. Have a good one. Enjoy your summer or winter if you're in the South.